Hello everyone. We for our application is built around the dengue disease analysis domain. So we selected uh, Sri Lankan dengue dataset, and we have built a dengue analysis dashboard, and it includes trends, forecasting, and hotspot detection. So if we talk about the project overview, it contains visualizing the patient count trends for selected district and time series forecasting of patient count using ARIMA model algorithm. And then hotspot analysis done by using clustering algorithms. So the first part is done by Vilochana, so I'll hand it over to him.
Thank you, Asankar. So let me share my screen first. So hope my screen is visible for you.
Yes.
So as Asankar explained, so our main focus is to forecast the dengue patient counts in Sri Lanka. So for the first approach, we have analyzed the trend of the dengue patient counts, and based on this trend, we have suggested the time series model, a simple ARIMA model to forecast the dengue patient counts in Sri Lanka. So moving on, so describing about the data source that we have gathered. So for this task, we have gathered data from the main council, the National Dengue Control Unit of Sri Lanka. So they have officially published the number of dengue patient counts for each district from 2010 to 2021 in the official website. So we have downloaded the dataset for each of the year, and we have combined all these CSV files to get a single set CSV file, and we have used this CSV file for our modeling and forecasting purposes. Moving on, the first part that I have covered is the trend visualization. The objective that I have done this is to capture the trend of the dengue patient counts for a certain selected district and a year. So I have given two parameters, district and the year. Once I have selected the district and the year, the trend of the patient counts for that selected district and the year is visualized. So the main objective is to analyze the long-term movement in the dengue patient count, so that if we have identified which period causes the most number of patients, and if we are alerted about the number of patients earlier, we can take the necessary actions as an earlier intervention. So these are two snapshots of the UI that we have developed. So moving on to the forecasting part. So as I have stated earlier, I have used a simple time series model and ARIMA model to forecast the patient counts for the upcoming 6 months. So here for this ARIMA model, mainly there are three parameters that I have to select: the P, D, and Q. So based on the values that I have given for P, D, and Q, the model forecast the number of patient counts for the upcoming 6 months. So once I have selected a certain PDQ value, uh, a parameter known as AIC, or the Car Information Criterion, is calculated for the model, and the model that generates the lowest AIC value is selected for the forecasting purpose. So this is one of the model that I have generated for the data set. Moving on, stating something more about the ARIMA model. The ARIMA model, or in other words, the autoregressive integrated moving average model, it is a statistical model that we can use to analyze the time series data and to capture the trends and the seasonality in the time series data. So as I have stated, there are three model parameters, P, D, and Q. So I have to select the values that matches P, D, and Q for the data set that we are working on. So uh, describing about the model selection strategy, I have used the range of values P, D, and Q. So the values that generates the lowest AIC value for the the lowest AIC value, and the corresponding PDQ values are used for the modeling purpose. So once the lowest AIC value is generated, it is selected as the best fit. Moving on, I have worked on a simple part for the clustering also. So this is mainly for a certain selected year. The districts are mainly classified um, according into three clusters. The number of clusters are determined using a method called elbow method. So describing about the elbow method is used to find the optimal number of clusters where we can where the data can be categorized into the cluster. So when the number of clusters increases, the WCSS value or the within cluster sum of square value decreases. However, we are selecting the elbow point where the WCSS value started to decrease slow. So moving to the demo part quickly. So this is the demo of the application. So once I have worked on this time series forecasting part, I have two parameters, the year and the district. So for the modeling part, I have selected 2020. So for the 2020, I have demonstrated how the dengue patient counts in the gold district varies on. So here we can identify what are the seasons where the number of patient counts is high, and we can take earlier actions as we want. So moving to the forecast model. So as earlier here the PDQ values that I have selected are 2, 1 and 2, and the AIC value is 1639. So this is the lowest AIC value that I can generate for the goal, the data set corresponding to 2020 goal. So for this, the forecasted values are given as a simple data frame. And moving to the district clustering report. So once I have selected the goal district, this generates the elbow method, and the point 3 is selected as uh, the optimum number of clusters. So when 3 is selected, the data set is clustered into 3 values. The zeroth cluster, which is having the least number of patients, 1 and 2, then based on the number of patient count. So here the districts that are belonging to each cluster are stated here, and the summary statistics are also given. So I'll hand over to Azanka to move on. Over to Azanka.
Okay, thank you, Lojana. So let me quickly go to my part. So my part is to hotspot detection the dengue cases. So what is hotspot detection? Is to identify dense dengue cases reported areas to it, so it will help in to stop critical areas and decide where to allocate resources in an effective way, uh, and uncover patterns. And if I talk about my part, it has two parts covering heat map and hotspot clustering. And the data set, as Vilochana talked, we had 2010 to 2021, and one more data source coming into my part of the application is geospatial data that is used to identify geometric boundaries for each district to uh, draw the clusters and heat map within our Sri Lankan map. So if I show the how it's look within the application, it will look like this. So all these boundaries and bordering the colors are done using the geospatial data. If I move on to the how we achieve that, first I have to prepare the data set. I had to apply some aggregation, cleaning, and merging to get the heat map. So we had each district as a column that we have to get the total cases column generated to draw the heat map first. And uh, so there were some when we uh, when we use that dengue dataset CSV file and geospatial data shape file, there was some inconsistency. So we have to get them into a common format. Some names were like not in the correct format, so we have to maintain those things, remove duplicates and aggregate those things, and drop some unnamed columns like that. So if I talk about the algorithm, I use a DBSCAN algorithm, because if I take k-means like algorithm, it will not match to my part of the application, because that k-means need initial set of clusters, and DBSCAN does not require that one, and it DBSCAN properly identify the dense areas and geographically close district into one cluster. So and it has something called epsilon value, which will use to identify the geographically close areas. As you can see, these um, colored bordered area are the 3 clusters. It's that geographically matching areas identified because of that DBSCAN algorithm, which was perfectly matched to my case. And here I have show some other clustering, flat and hierarchical clustering. Finding the hotspot with DBSCAN. So we gave standardized district centroid, which are XY coordinates, into the DBSCAN algorithm, and got as output clusters 0, 1, -1. So if I talk about what's another problem in the when I explore with the k-means, k-means gives -1 noisy data points as its own clustering. So it draws borders around all the districts, which is not what we want. We need the dense areas to as clusters. So that's achieved by DBSCAN, because it has this epsilon value. So if I talk about the epsilon value, I use 0.6 to get these clusters. If I reduce below 0.6, it will create less amount of cluster, like all this area into one cluster. So if I increase more than 0.6, is also going to create noisy clusters. So these epsilon and minimum number of sample as 3 gave the correct values for the parameters to get the best result. And this geospatial, if I talk about the geospatial data, putting results on the map, that cluster labels I got from the above step, uh, I used to create the as a new column in the GeoIS data frame, and then that link cluster labels uh, used to using the geospatial context, the district name, its shape, and its total places. This step is allow us to visualize the clusters on a map and identify which specific district belongs to each hotspot, as you can see in this Sri Lankan map. Let me move on. Uh, so we use Matplotlib, GeoPanda, and to get the heat map, and we use DBSCAN algorithm to generate the map inside the Streamlit application. And if I talk about the result, the main goal of this app to turn raw data into a useful insight that can help people to make better informed decision. And that objective it achieved. So we can use available so we can allocate available resources in the best possible way, take necessary action when we in the dense areas, and focus less on the very um, less amount cases areas. And what did I learn? If I talk about the learning outcome I took, I realize how important is the data set, and how small inconsistencies in data set can create problems. Hello.